In this session, we have 3 invited talks, and the first presenter is Alejandro Torres Forné, and the title is The Understanding Proto-Neutron Star Oscillations in Quark Club Supernova. So please start.
Okay, can you hear me fine? Okay, good. First, I want to thank the organizer to organize this very nice meeting. I really enjoy it. I was asked to give like a brief overview about the asteroseismology part. Many parts of the things I'm going to say has been presented in different talks during this week. My idea is just to put everything a bit together and give a bit more details about how the modes and everything related to this are computed. This work, the last part of my talk will be some parameter estimation work we have done. And everything I'm going to present here has been done in collaboration with these 3 great young scientists, Dimitar Semiklidou, Noah Wolf, Tristan Bruel, and not so young, but very great senior researchers, Marianne Bizuar, Patricia Maturana, Renata Karl Frolik, Werner Müller, Martino Begauliger, Andrea Passamonti, Paolo Cerdà, and Tony Font. So we have been seeing this plot many times. I'm not going to spend much time here. Bert has, in this amazing talk on Monday, explained all the details. Also, Tony today. Sorry, I don't have time to put our knowledge here. Sorry, Tony. But I'm going to talk all the time about the proto-neutron star phase and during the collapse. We already know that we have the proto-neutron star surrounding standing across in shock. Both the proto-neutron star and the shock has perturbation that produces the source of gravitational waves, different size of different regions of the star. And well, it's not going to, I don't want to spend more time here. I should say that when we started this project of asteroseismology during my PhD, almost 10 years ago, I feel a bit old now, the idea has been always to do parameter estimation with the core collapse. I mean, we know for different groups, different simulations, different groups, that the gravitational wave signal is stochastic. This doesn't allow us to use the template bank search that could be done in compact binaries. But when we compute the time frequency domain, we have these arcs, F mode, G mode, high frequency feature, whatever name you want to use it, is fine. This arc we saw in all the spectrum. Choose your name. So our idea has been always to do, we can do something with that. We can get some information from the progenitor using these gravitational wave signals. So this is the main goal, and this is what I will show you at the end. Just to give you a bit of a history about how this field has been evolved in the last years. This is not very new. In Riesneger and Goldreich in the 90s, they have the first derivation of the equations to asteroseismology using simplified backgrounds. There is many other works related to that. It was in 2018 when Sotani also did a step forward, giving a background based on simulations. And during my PhD, what I did is to extend the equations that Andrea Passamonti derived using background directly from the simulation. We use the simulation, we get the background data, and we do, in principle, in Cauchy approximation. We don't perturb the metric. After that, this is the work from Morozova collaborators when they add also perturbation on the last factor. And finally, we add to this study the perturbation of the conformal factor. That I don't have time, but I can see you that it produced different results. Also in 2018, we published our great code, which is General Relativistic Eigenmode Analysis Tool, which is publicly available, and we are still developing things, adding more features that can be downloaded with the web page. After that, this was the work with Mr. Natcher and Snyder in 2020. They add the pseudo-Newtonian analysis, which is more set for using simulation that use Newtonian pseudo-Newtonian metric. In 2019, we used the result from GRADE for different simulations to derive some kind of universal relation. I will explain a bit later, also Sotani 2021. And the last step we do in this field is the nice paper from diameter, that we relax the hydrostatic equilibrium and we include accretion. Just again to fix what is the math of what we are solving a linear perturbation analysis in the form of an eigenvalue problem. We have the background, we get the perturbations, and we derive the different eigenfunctions, imposing different boundary conditions and different positions. This is possible with different groups and also with great code. What is the steps? What is the line of thinking we have at the beginning? We have a multidimensional simulation, like this one from Martin 2013. We compute the waveform, we get the spectrogram, and what we try to do is to do the analysis to see if the spectrum of the modes coincide with the gravitational wave emission. This is the step we do. We have an angular average, because the equations up to now are 1D. We need an average. And we compute the spectrum of the modes, and we compare with the gravitational wave emission. Seeing in this work we have that some of the modes correspond almost equally with the trace of the gravitational wave signals. However, I should say a few things. This is the result that Grace produce, or any code produce. We solve the modes for every time step of the simulation. So the code produce a bunch of frequencies or eigenfunctions, but there is no relation between them by the code. This is a second step, has to be done we can recognize here different patterns, different traces, but the code itself doesn't give you any idea about that. You need to trace essentially by hand. You need another step to trace the modes, to see how they evolve in different frequencies and different times. So this brings the question about what type of modes we can find. According to the theory, we will see gravity waves that produce by buoyancy. They are transverse waves, and we call these G modes. And in the other side, we will have pressure waves that are longitudinal, and we will call it P modes. And the restoring force is pressure. This is what theory about modeling knows. And in the work from Cox in the 80s, he presented this propagation diagram that allows us to understand what is P mode, what is F mode, what is everything. So according to this, we can identify two different regions: the acoustic regions, where the frequency of the modes we saw are higher than the Brun-Weisshall and the Lang frequency at the same time, and another gravity wave region, where the frequencies of the derived modes is lower than both Brun-Weisshall and Lang frequency. Imposing our knowledge about P modes, G modes, we can identify these things. We can see that what we call, or is called F mode, is the first P mode because it propagates in the acoustic wave region and has 0 nodes. The P modes has increasing number of nodes as the frequency increases, and the G modes are in the gravity wave region and have increasing number of nodes as the frequency decreases. Okay, we are reaching from nodes to 0 and from 0 to 1. And this is essentially the nice picture of this. If we go to a real simulation, we have this kind of plots for a given time in radius. So we can have gravity region, acoustic region, we can identify the modes for this, but you should think we have thousands of time steps sometimes. If a simulation with 1,000, we have to trace the mode using this, will take a lot of time. If we want to do some general things, we will analyze a lot of simulations. So using the regions for tracing the modes could be very painful. If we go to the spectrograms, I want to give some ideas about the avoided crossing. Avoided crossings is something that has been said in the literature, in the nuclear physics and quantum physics, is well known. And I want to put an example for today to understand how this works in our case. We have the simple equation for two coupled oscillators, which the frequency depends on a continuous parameter, in this case lambda. In our case, can be time, can be density, can be whatever, but they compose. So they have analytic solution, which I'm showing here. If we plot the frequency in function of lambda, we have this kind of, oh, it's not moving, sorry. This is what I should use the PowerPoint. I will explain by hand. when we do that, and we have a coupling parameter alpha in this matrix. When alpha is 0, we have two independent modes. And we trade the frequency with lambda, we will see that they cross completely. Okay. If we get the eigenfunctions of these decoupled modes, we will see the eigenfunctions are changing continuously, but they change in frequency, they cross. When alpha is not 0, we can see, I was hoping that it was working, that the frequencies, we trace the frequencies, we can trace this individually because we can compute, they start to separate to each other. They are about to cross. So if we keep the tracing, we will see that the frequency in red, for instance, go like a small curve, and the blue one goes a small curve up. But the eigenfunctions of each mode, they cross. The frequency don't, eigenfunctions yes. And this is why I want to put this quote, which is directly extracted from this book from astereosismology, the book from Aerts, Christensen, Delgard, and Kurtz, when they say, at the Boyd crossing, the two modes exchange nature while they stay maintaining the original labeling. So if we label the modes like the frequency we have here, what we see is in the Boyd crossing, the nature will change. So we have two options. Keep the labeling, which is completely fine, and change nature, or keep nature and change labeling, because it will happen in the Boyd crossing. In realistic simulation, in our analysis, we see this. We see a bunch of avoided crossing with the modes that increase in frequency. I don't want to talk about anything about the nature, and the modes that go down in frequency. And there is not only one avoided crossing, what we refer, this is also seems to be related with the power gap. This is the big one, but there is a lot of avoided crossings in this method. In this here, it's clear, if we look in logarithmic scale, you can see that there is, in this case, many avoided crossing in a series, and another case, we have just crossings of the modes. With the effect, I will show you later, that if we just believe in the number of nodes, when we have a real crossing, the number of nodes can change. I saw this in many times. I asked Daniel if it's a very nice talk. I take this directly from his, and I can see what they do, a very good job. I like this paper a lot. They see in this analysis that there is avoided crossings, and they have this nice picture. They trace the two modes, two eigenfunctions, before and after the avoided crossing. If we see, we keep the labeling, which is, I said, completely fine, but if the eigenfunctions have interchanged. They are not the same because they depend on a continuous parameter. It's not going to be the same shape, but you can see, if you trace a bit, that what happened is the avoided crossing is keeping the labeling, the eigenfunctions interchange. So this gives us to another step, which is the classification. How do we trace the modes? We did, this is from our paper in 2018, which essentially corresponds with a nice paper with Rodriguez et al. There are essentially three ways to do that. We can go to the number of modes, which is easy to do. It's easy to do. So it's the most, but has some problems. For instance, you can see in this spectrum that the blue, the yellow and the green, that the shape is completely different. If we use only number of nodes, we mistrace them, because you can say the shape that is more or less flat, but the green one has a lot of oscillation because it's a mode which is on the short position. The short position in this simulation changes a lot because there is a very weird grid, and the oscillation is this. This is what happens with you use only radial modes. Also, if you don't find the zero node, because can be times when there is no zero nodes even functions, you cannot label the other modes. The next step, or the other thing, is to use what we call ISO classification. Has another name in the paper, but essentially the same. Use the eigenfunctions, also phase and shape, to correctly trace the modes. Again, it has some other problems. You see when the modes cross, the number of nodes changes also, because it's an effect not well understood, but it happens. So this brings us to the last one. The last one is what we call matching. It's what they call, I don't remember the name nowadays, but we can trace the mode using the shape of eigenfunctions and also the trend of the frequencies we are saying, just to cross the avoided crossing. The bad thing about that, I mean, they are different. I think this is correct, is better, but it's more complicated to compute because you need to do more things. So, given that, is this question: what we can learn from astereosismology, what we can relate with the number of with the progenitor parameters. In this work with Pia Jacobus and Bernard Müller, they do different simulations with different equations of state, and they identify two different modes in the spectrum. One is the dominant mode, F mode, G mode, whatever you want to call it, which always appears. But in this case, they saw this mode that goes down in frequency, which depends directly from the equation of state. They call it Corgi mode, and you can see that the shape, and also it appears or not, depends on the equation of state you are using for the simulation. So if we see this mode in a realistic gravitational wave signal, we will be able, in principle, to relate with the equation of state. Related to this, not directly, but is our universal relations, what we use. We call it universal because we use 26 simulation 1D, 2 different codes, 6 equations of state, and 8 progenitors. And the thing is, we put these relations with this, the surface gravity of what we call G2, but is the dominant mode. You can see that essentially the points get together up to some error. We call universal because this relation doesn't depend on the equation of state of the progenitor of the code. It's not it's something we can do. And also, Sotan and Tokiwaki in 2020 do similar thing, but they found that the relation is the mean gravity, mean density. And Hajime will explain this in the next talk with more detail. But I just want here to explain a bit how I compute the fits and why I think the difference comes from, where the difference comes from. The thing is, in D2, we have different classification methods. We use matching, and Hajime, you can see this, use the same one that doesn't cross, about the crossing, which is fine if you know what you're doing. Also, there is difference between the models. In our case, using coconut or Aenus Alcar gets slightly different things at later times, so this produces more dispersion in the fit. And there is the main thing. When I compute the fits, I try to do like combination of 5 variables, mass, a different size, different places. The best fit is none of this. The best fit is something between. I mean, you put, it's a number, it's not R over 1.5 or 1 over 2, it's something in between, 1.72. This is what I said, that you get, depending on different fit, you get a different error, different fit, but it's none of them. We choose this one or the other one because we know by advance that this should be there. It's this kind of relation in advance. But the best fit is none of this. Numerically speaking, only, is not none of these fits. This is why both, more or less, coincide in the results. Well, as I mentioned at the beginning, our aim was being always to do parameter estimation. So in this work with Marianne and Tristan Bruel, what we do is the inverse method. We have a gravitational wave signal injected in Gaussian noise, and we get a method, we derive a method to extract the trace of the mode, and then use universal relations to get the evolution of the mass over radius. This is the inverse problem. I mean, it's the parameter estimation we can do right now. In this work, we use different simulations from 2D and 3D, from Martin, different progenitors, equation of state, and we injecting noise in the second generation, combining LBK, all of them, also in ET and Cosmic Explorer. I know our observational scenario is, we know we have a neutrino trigger, so we know in time when the explosion occurs, and we have an accurate sky localization by electromagnetic counterparts. It's a simplified scenario, but it's something we can do. So with this, essentially what the method does is to get a function of frequency over time. And we can trace this. So when we do that, we can use universal relations to get the evolution of the surface gravity in function of the time. Here, we can see in this example from the paper that when we do that, the true ratio that we can derive directly from the simulation are within the error bars of the model in all the times. We will that for different network combinations, for different distance. At some point, but the farther the source, more complicated is to trace the frequency correctly, and this start to deviate. But for a well-powered source, we can get essentially the trace. We can argue the model has to improve, of course, but by to now, we can do that. We can do parameter estimation with that. Reduce, yes, but we can. The other work I want to show was produced by Noah Wolf in 2023. He came to Pablo and to me, but it was more than 1,600 simulations of Corcola supernova with different progenitors, different equations of state, different metallicities, a lot of things. And he was using GRADE and has some problems with that, so we help him. So this is, for me, one of the main results of this paper. What he does? He traces the modes, put the labeling he wants at the moment, F mode and G1, and he identified that tracing like this, in the different equations of state, you get different trends. I mean, at 0.4, with the avoided crossing more or less happens in all the simulations in this case, you can see that in this classification method, you get this change of shape. So what he does is say, okay, I will look at this time. I will look for two fundamental modes, the F1, the F, and the G, and I will get the frequency of both, and see if these frequencies are related with the equation of state. This is the plan, okay? And what we get? He uses a custom Gaussian mixture for all the simulations to produce these histograms. What depends on the equation of state. If you see, this is the mean value of the first peak, in the first of the fundamental mode if you want. Oh, no, sorry, the G1, the ones go down in frequency, and you can see like they have some relation with the equation of state for 1,000 simulations. There is quite a spread, metallicities, many things. Some of them, of course, are, some of them are overlapping. I mean, we cannot distinguish very well between NL3 or TM1, but the ones for H, 0 and X, have a very separated way from the others. So if we were able to measure the avoided crossing, the power gap, the frequency of the power gap, we can get some information about the equation of state. This is the idea of this. Okay. Of course, this needs more work, more simulations, more to confirm this, and also we need to derive at some point the inverse problem. Get the waveform into noise, try to extract this frequency, and see if we can derive the equation of state for that. I don't know if I go too fast. Maybe yes. Okay, but these are my conclusions. So the idea of this talk, as I said at the beginning, was to put everything we have learned these days about the theory, about the different methods to make inference about the modes. What I want to do is just to try to give you an idea of what is the technical things, how we compute these modes, what are the things we have to face. And the tracing of the modes is one of the most important things, and also the physics we impose, as Tony was mentioning in his talk, and we have to reduce and better the models. But there is also room to understand why different groups have different results, because it depends on how you classify the modes, because the code doesn't give you this. This is the main conclusion, okay? Just the first part is something we learn from all the talks, but in the other part is something that we want to do. We need to improve the eigenvalue calculation to include SASI, which is what Dimitri's work has been doing. In the future, we will also include rotation, extends to 2D at least, the equation. We need to improve the eigenvalue classification because classifying the modes is very computationally costly. It's something that we do in our universal relation by hand and takes several hours per model of Pablo just changing things to get the correct trace. So this is why we don't extend to thousands of simulations. This should be improved. I mean, I have been working a lot in the classification. We should include the inference for the future, like the power gap, like the secondary G modes, the SASI modes, something that can disentangle the difference between mass and radius, or equation of state. And in this case has been already done by Pablo, which is the include of numerical templates that include rotation later and do this kind of parameter estimation. Thank you.
Okay, I think we have time for several questions.
Alejandro, thank you. Magnificent. This is exactly what we needed. Can you go back to the slide you had with the histogram there? Yeah, that one. Yeah. So it's interesting. I just might want to make a comment. You know, what differs SFHO and SFHX differ from the rest in that it's the only equation of state that develops its parameterization of the nucleon-nucleon interaction in the relativistic mean field model based on neutron star observations, neutron star mass and radius observations. And it's interesting that it's set off from the rest. With regard to the rest, as you know, some of the ones like TM1 and L3, they're already been ruled out. So it'd be great to fill that out a little more with some of the others like DD2 that are still, because those, I presume they will still keep clustering, but I just had to note that the SFHO and SFHX are different, and they're different for a reason, because we're using actual astronomical observations to constrain the microphysics and then in turn the EOS.
I mean, this, we don't have any control about that. I mean, NOAA came with the simulation already done. So they select the equation of state they wanted. But the interesting thing is, even in these ones, you can see a slightly difference on the frequency of that.
Thank you, Alejandro. I had a question about this as well. You mentioned, moving forward and doing this in simulations with LIGO noise. I know this is a hard question to answer, but I guess what are your thoughts on, I guess, identifying where this avoided crossing would happen from a signal point, signal detection standpoint?
I don't know if my colleagues agree, but sorry. Looking for voids in the data is more complicated than seeing power, because if dominated by noise, we cannot see something that goes to zero essentially. So I don't know if you, Jade, agree with that. Maybe. The thing is, maybe we need a very clear signal to identify when there is no signal. If we have two modes, we can see the gap or infer the gap. If we see only this one, I think it's more complicated sometimes. We see those, in the ones from PIA, here, you can see more or less where the gap is. You see the two modes, you can infer more or less when they are going to cross, and you can get more or less. How is this with a lot of noise? Something we have to try. I think it's complicated. Not impossible, but complicated. Well, we need some work, you have two modes and this kind of thing.
Hello, thanks for the nice talk. I just have maybe this is a naive question, but you had the picture showing what an avoided crossing is with the red and blue lines with this frequency versus parameter.
And it was supposed to be a GIF.
Oh, I see. Okay, because I'm just quite confused why those two frequencies are touching, because we're not.
No, it's because it's alpha 0.
Okay, I see. Okay,
but in my PowerPoint, it was I didn't realize when I go to PDF I will lose this, which was the most important GIF in all the presentation.
Okay, no problem.
But I can show you when you increase alpha, this starts to bend and to separate.
Yeah.
And the separation, I haven't said, depends on the coupling factor.
Okay, great. Thank you.
Thank you so much for your presentation. A question I have is that you said, if I heard you correctly, that you don't believe that these frequencies are directly related to the specific exponents of m over r squared. You think it's a different power, a slightly different power of r, m to the over 2.5 or something?
I don't say that. What I said, let me give is the numerical fit doesn't correct. The best numerical fit is none of them. It's something in the middle. So this is, in my opinion, why both relations were more or less the same. They differ on some points, but they are parts of the thing that essentially give you the same result, because none of them are the exact numerical best result. The numerical result is another one.
Okay.
At least when I compute my universal relations. I don't know, Hajime will explain later. But for me, when I do brute force approach, combining different exponents, different variables,
Mhm.
the best fit is something which was essentially between them.
So in between the surface gravity one and the dynamical frequency one, like between over r squared and over r cubed?
Mhm.
Oh, cool.
Okay, then let's thank the speaker again.